Good afternoon, everyone. Welcome to Taco Tuesday. My name is Brett Zerba, and I'm an applications engineer with Taco, and I also do some training on the commercial side. I will be moderating today's presentation. Rich Medairos will be the main presenter. I will give him access, or he will start very shortly. So let's go over some of the ground rules and ground strokes and everything else that we have to. If a couple of you can raise your hand that you can hear me and see the screen, I would appreciate that. Or let's see, we get any hand waving? Any raising? Uh-oh. Oh, wait, there's one. Thank you, William. Appreciate it. Appreciate it. All right, and Tori did too. So we are in good shape and off and running. As has been the case with these Taco Tuesdays, the last, God, almost 3 years now. It's kind of crazy. Hopefully the light is at the end of the tunnel. Not sure which way it's going yet. But anyways, about 24 hours after today's presentation, you'll get a email, or you should get an email with access to your PDH and a copy of the presentation is being taped, so you'll get that access to that as well. So
Brett, I'm just looking quickly here to see where it says it's being recorded. I don't see where it's being recorded. Do you see that on your screen?
Did I not hit that?
I don't know. I just don't see it. Usually there's a message that said it's being recorded.
I'll make sure. Options, view. Recording is in progress. I see it under view, Rich, so it is in progress.
Oh, good.
Yeah, thank God. Yeah, we do lose track of our minds every once in a while. And our friend Zach and Maxwell it says it's being recorded at the bottom. So this session is being recorded.
Oh, I see it. It's way at the bottom. Yeah. They must have moved it. I was looking at the top.
We're out of touch. We haven't done one in a couple of weeks, so
we forget which buttons to push.
Now I forgot what I was saying. Oh yeah, access to this, access to that. Welcome to Taco Tuesday, and hopefully everybody knows a little bit of Taco's history. 102-year-old privately held company, third generation. I recognize some people's names on this list, and I know you've been at our factory recently, and so you've actually met the owner, Johnny White. He pops into some of the classes we have at Taco. And he popped in last week, and he had a guest with him who was out on a factory tour. And for any Seinfeld fans out there, he had Peterman, John O'Hare, whatever the actor's actual name is, but Elaine's boss on Seinfeld is a friend of Johnny's, and he was at the facility taking a tour, and he actually went to Providence College, I guess, for some part of his undergrad or something. But nonetheless, Peterman was at Taco when he popped in and said hi to the class we had in last week. So you just never know what you'll come across when you visit Taco. John O'Hurley, thank you, Paul. I knew someone would know his name because I always forget, but I did love that show. I will have to admit, that was one of my favorite shows. Also, in addition to Johnny, Cheryl Merchant popped in, and she's our global CEO, and Cheryl told us all about some exciting happenings at Taco. We have some big expansion plans at our facility in Vietnam, at our facility in Fall River, at our facility in Cranston, and one other facility, I think, in Italy. So big capital investments. The company is really looking to expand and is expanding. Very exciting for everybody. So that was pretty neat to hear. Anyways, today's presentation is on chiller plant equipment performance, piping, maybe a little piping arrangements, but and the equipment that goes in there. And we're not going to get, well, I'll let Rich get into the weeds on his presentation. Looks like Rich just drew a car, because I know he's a car guy. He's a gearhead. I mean, one of the first times I met Rich, he's showing me some pictures of his garage, and I'm saying, what is all that stuff? He had taken apart his wife's engine and labeled every part, because of course you have to take it apart to put it back together, and you have to label all the parts, because I think there was he had to rebuild it. So God forbid, if you don't label everything properly, you'd never put it all back together. So he's quite the guy. But I'll let him introduce himself. By the way, next week on Tuesday, I have been invited to a luncheon at Taco, a service award luncheon. I will be getting my 25th year service award for Taco. So sometimes they do it after work, but this particular one's going to be a luncheon at work. So it's like the 5-year thing, 5, 10, 15, 20, 25, 30. One year we had someone with 50 years, believe it or not. Good old Tommy Lawrence and others probably. So service award, I'm looking forward to that, to heading into the office next Tuesday. So I think I've yapped enough. My friend Rich is ready and willing and able, and please ask questions. I'll be monitoring the questions. And Rich, take it away.
Thanks, Brett, for that great introduction. Today we're going to talk a little bit about chiller plant equipment and performance, and also about piping design for chiller plants. My name's Rich Medairos. I'm one of the engineers here at Taco. My specialty is engineering design of HVAC systems. I am a PE registered in a couple of states, and I've been at it for a few years. So let's get into today's discussion and talk about some information about chiller plants. So we're going to talk a little bit about chiller plant energy usage. We have some equations and formulas. Since this is going to be recorded, I won't spend a lot of time on these equations and formulas, but they will be on the screen and you can use them as future reference. We're going to talk a little bit about air-cooled chillers versus water-cooled chillers. And we're going to talk about cooling towers and then pumps, which includes both chilled water and condenser water pumps for today's discussion. And as Brett said, you don't have to wait till the end of the presentation. You can ask questions anytime. He'll be monitoring those questions and he'll ask me to pause periodically to answer some questions. So let's go into chiller plant energy usage. So it turns out we got this nice slide donated to us by Johnson Controls. Thank you very much from the guys over at Johnson Controls. And they put together this little little chart that says for a typical, excuse me 1 second, Brett. I'm going to have to bear with me 1 second. Okay, I'm back. They put together this nice little chart for a typical simple office building. About 38%. Oh, let's see if I can get this thing to right here. Ooh, what happened? Boy, that was cool. It just flipped over. There we go. 38% of the energy consumed by a typical commercial building is for the HVAC system. The HVAC system. So out of all of the energy consumers in a building, 38% is for HVAC. By the way, I just point out, if you notice, lighting is around 26%. So you'd be amazed at how much energy goes into lighting these days. But HVAC is still the winner, still the one that's going to consume the majority of energy. All right. And out of that 38%, the chiller plant, and you can tell right here, the chiller plant's about 35%. The boiler plant is also about 35%, but that number varies. If you move, especially in the United States, if you move closer to the south, that chiller plant percentage goes up and the boiler plant percentage goes down. So even though in terms of overall averages, the chiller plant is actually probably the dominant energy user. And of that 35%, the chillers make up roughly 64%. The pumps are about 22%, and the cooling towers, if it's a water-cooled system, and we're going to talk about both air-cooled and water-cooled for a couple of minutes, but we're going to focus our attention mostly on water-cooled because that's where the majority of chiller plants are these days. Well, I shouldn't say the majority. What I should say is that in many cases, chiller plants are water-cooled because they can have a significant energy-saving component, and we'll talk about that in a minute. Okay, so let's dive into the chiller first. And let's see if we can erase this. Yep, we can. Look at that, Brett. That's amazing.
Off to a good start.
Yeah, so again, for the equations and formulas, I'm just going to put them on the screen. I just want to highlight a couple. This one here, the one at the top of the screen, is probably the one, a variation of that is the one that we use most in the hydronic world, and that is we're interested in what's happening with the flow in gallons per minute. And if we have the load in BTUs per hour, we divide that by the delta T and by 500, that's how we can get the GPM. So it turns out that one of the things that we're interested in knowing is if our delta T, I'll make a diagram here, I mean a triangle, delta T, if that happens to be equal to 12 degrees Fahrenheit, it turns out that if we have 1 ton of refrigeration, it turns out that at 12-degree delta T, and we plug it into this formula up here at 12,000 BTUs per hour, we get 2 GPM per ton. And that's kind of a useful, easy number to remember. So again, if you have a chiller plant and you're delivering water, for example, let's just make up an example. Let's say you're delivering water at 42 degrees Fahrenheit and you're returning water. So we'll make that supply. And then the return water is approximately 54 degrees Fahrenheit. That's a delta T of 12 degrees. And that means we're going to use 2 GPM per ton for a chilled water distribution. And again, I'm not going to spend a lot of time on the formulas because we are recording this and you guys can see this later on. And again, here is some more information about some formulas. We're going to focus our attention on the COP a little bit later on, and we'll come back to this. But again, I put it up on the screen so that when you look at the recording, you'll have information about that. A couple of other quick tidbits of information. The density of water is approximately 62.4 pounds per cubic feet. And the reason I put that up there is because it's a good number to put in your basket of easy to remember things. And again, that's clear water. There's nothing in the water. It's not salt water. It's not water and glycol. It's just clear water, and it's at approximately 70 degrees Fahrenheit, give or take a little bit. And that's the density of water. And 1 gallon of water weighs about 8.33 pounds. And another good number to remember is that a cubic feet of water is about 7.5 gallons. And that the conversion for BTUs per kilowatt hours, there's 3,412 BTUs per kilowatt hour. So if I had, say I had 1 kW, I'm just going to obviously make this very simple, then that 1 kW is equal to 3,412 BTUs per hour. Some useful formulas, they're good to know. Not going to spend a lot of time on it. Okay, let's move along here. So let's talk a little bit, like we said, about chillers. There's 2 major categories of chillers that are used in chiller plants today. The one on the left is an air-cooled chiller. The one on the right is a water-cooled chiller. What are some of the differences? Well, let's state the obvious. Air-cooled chillers reject their heat to the atmosphere. So this guy here has got fans at the top. It draws air into the condenser over here. I have some arrows for drawing the air in, and it exits out the top using these fans, propeller fans. That's how most air-cooled chillers work. And the ambient temperature, let's say that the ambient temperature is somewhere around 95. It could be higher, but we're just going to pick 95 just for the fun of it. If the ambient temperature is 95 degrees, that means the condenser itself has to be at a higher temperature in order for the heat transfer to take place. So basically, we're rejecting heat at an ambient temperature of about 95 degrees Fahrenheit. And their efficiency is, or the amount of power that an air-cooled chiller typically consumes, is somewhere between 1.25 and 1.5 kW per ton. Now, when we talk about water-cooled chillers, ultimately, let's assume for a moment, let's see, this is the compressor here. This is probably the condenser down here. We're rejecting heat to condenser water. And we probably have an entering condenser water of 85 degrees Fahrenheit and a leaving condenser water probably around 95 degrees Fahrenheit over here. By the way, if the air is coming into the air-cooled chiller at around 95, it's probably leaving up here anywhere from 10 to 15 degrees. Let's say it's 15 degrees, so that would be about 110 degrees Fahrenheit. And the amount of energy that a water-cooled chiller consumes is significantly less. It's somewhere in the range of 0.5 to 0.85 kW per ton. Now, obviously, some manufacturers are going to be a little bit less energy consumption, and others will be a little bit more. We're just looking at sort of orders of magnitude here, just to get us oriented. So, since a water-cooled chiller is significantly less in energy, we're going to focus our attention on water-cooled chiller plants today. Any questions out there, Brett, before I go into a little bit more detail about water-cooled chillers?
Yeah, we do. You says has a question. Generally speaking, I think, what's a threshold tonnage in your opinion of air-cooled versus water-cooled?
Well, I think I've seen the packaged air-cooled chillers are in the order of magnitude of around 300 tons. Now, I think you can probably have a custom-built air-cooled chiller that's larger than that, but 300 tons is about the average for, say, a packaged air-cooled chiller. That's about as large as they get. On water-cooled chillers, they can go significantly larger. There are some projects out there that we've looked at recently that I think they're over 2,000 tons per chiller. So there's a huge difference in terms of potential capacity.
There's a couple of questions associated with energy. When you're talking about kilowatts per TR for water-cooled chillers, someone is suggesting you probably should add the fan power and pump power in order to see the real numbers.
Well, actually, that's a very good point. So these numbers here represent, on the water-cooled side, they represent just the chiller. And we're going to actually add the loads of the other components, the cooling towers, the pumps, so you can get a picture of what the total kW per ton is. But most of the time when we think of chillers, we think of packaged air-cooled chillers as the total power, and we think of the water-cooled chillers as a standalone component. But you're right. You would add the power of the pumps and the cooling towers to get a full plant picture of what's going on.
Yeah, other folks are making that same comment, so I don't think we need to get over those. But our friend Darren McPherson, good old Darren.
Hey, Darren, how you doing?
Yeah, although some of the air-cooled screw manufacturers are approaching upwards of 600 tons now, are now approaching. So anyways,
600 tons. That's great. That's good news. They must be fairly large physically. Maybe he can type in what he sees as sort of length and width of those things. That's a good size.
Yeah, Paul is saying they can train and JCI go up to 550 or 575. So it looks like all the big boys are approaching 600. So I'm sure physically they're big, but nonetheless, that's what they're looking. That's what some of the folks are.
Yeah, I'm going to make a note. So these guys over here, the air cooled, they can get up to around 600 tons. And
30 fans.
Holy mackerel.
Is what Darren said.
That's a lot. That's a lot of fans.
Well, makes sense though, right?
Yeah. Okay.
All right. We're clear.
We're clear. So let's go on. So let's talk a little bit about a water-cooled chiller. And again, you can certainly find water-cooled chillers that are less than 0.5 kW. Whoops, what happened here? It's always pressed the wrong button, Rich. Water-cooled chillers, you can certainly find them less than 0.5 kW per ton. You can certainly find them slightly more than 0.85 kW per ton. But I kind of like this mid-range right here. And the other thing to consider, again, these are kind of starting numbers here. You can certainly find chillers that are more than 85% efficient and also obviously less than 75% efficient. But I'm looking mostly at what the overwhelming majority of equipment is in the marketplace. And as the cost of energy increases on a daily basis, manufacturers are going to make their equipment more and more energy efficient. I mean, there's no mystery. I mean, if you take a water-cooled chiller, for example, and you make it physically larger with respect to your heat exchangers, you can increase the overall efficiency, but that increases the first cost. But certainly as the cost of energy goes up, you can offset some of that first cost in a reasonable return on your investment. So, you know, this is a sliding scale here in terms of efficiency, which also is affected by the cost of energy dollars. So as the energy goes up in cost, the efficiency of the machinery gets greater. And that's fairly common. We've seen that through the millions and billions of years that they've been making. Well, they haven't been making them for that long. Okay, not when it comes to the extinction of dinosaurs 65 million years ago. All right, so let's look very briefly at what affects the efficiency of a chiller. The chiller is, so here is on the left side is our water-cooled chiller. And in the middle, we have a very simple diagram for a water-cooled chiller, the refrigerant diagram, which also includes the cooling tower. I've got that marked up here, and also where we have the primary chilled water. I'm going to go into a larger diagram so you can see it. And we're also going to talk a little bit about the pressure enthalpy diagram. This is a pH pressure enthalpy chart over here. And I want to point out that this is for refrigerant R134A, which is a very popular refrigerant that's used today. So let's go to the next slide and focus a little bit on the refrigerant cycle as it pertains to a water-cooled chiller, So let's start at the compressor. Here's the compressor, and the compressor is compressing the refrigerant. The refrigerant starts off at the entrance of a compressor, rather. There's a mouthful for you, Brett. It's a low temperature, low pressure gas. It's a gas. Okay. And the responsibility of the compressor is to change the temperature and pressure of the refrigerant. So what's inside this green line pipe here is the refrigerant. When it exits the refrigerant, I'm sorry, when it exits, I have to say that again in English words, Brett. When it exits the compressor, the refrigerant is at this point here is a high temperature, and here's the important thing, HIGH, high temperature, high pressure gas, high pressure. And again, it's a gas. And one of the things that manufacturers try to do is they try their best to make sure that the gas enters, that the refrigerant rather enters the compressor as a gas and leaves the compressor as also a gas. That's important because if liquid gets into the compressor, it could really, really harm the compressor. So since it leaves the compressor at a high temperature, high pressure gas, it can reject its heat through a water-cooled condenser. So here's the condenser. Refrigerant is going to exit the compressor and enter the condenser at virtually the same set of conditions. And then it's going to reject its heat to the condenser water. In the next slide, I'm going to show some temperatures. And then it turns from a high temperature, high pressure gas to a high temperature, high pressure liquid. So it leaves the condenser as a liquid again, but it's also at a high temperature, same temperature and pressure, HIGH, high temperature and high pressure, but this time it's a liquid. All right, and when we look at the pressure enthalpy diagram, you'll see that the process across the condenser, the refrigerant process across the condenser, is a constant pressure process, constant pressure. And then here's the magic, one of the magic things about refrigeration is that when this high temperature, high pressure liquid passes through the expansion valve, it exits the expansion valve as a low temperature, low pressure. All right, this is a mouthful, Brett.
You're working on it. You're working it.
Mostly liquid, not 100% liquid. We try to make it as much of a liquid as possible. Mostly a liquid. That's why I put in mostly. That mostly, M-O-S-T-L. That doesn't even, that looks like an F, but that's mostly a liquid. And then when it gets into the evaporator, that's when it absorbs heat from the return water temperature. And this is a chilled water system. So this supply, primary supply and primary return, that's your chilled water that's in your system. That's called the chilled water. All right. And so it's going to enter the evaporator as a liquid. And as the name implies, the refrigerant is going to evaporate as it absorbs heat from the chilled water. It's going to reduce the supply water temperature. In a minute, I'm going to show you. Then the cycle starts all over again, because when it leaves the evaporator, it's now a low temperature, low pressure gas. And that's the basic refrigerant cycle. Isn't that the coolest thing ever? Oh, I made a pun there. Cool thing. All right, how are we doing for time? We're just about on time here. So now let's add some temperatures to this little guy. So typically, not typically, but in today's discussion, remember we said our delta T is going to be hovering around 12 degrees. So there's our delta T. It's 54 minus 42, and that's equal to 12 degrees Fahrenheit. So there's that 12 degrees we talked about down here. All right. Let's see. And then also, the condenser water temperature, we're going to have water entering the condenser from the cooling tower at 85 degrees Fahrenheit and leaving at 95 degrees Fahrenheit. Now, in order for heat transfer to take place, the refrigerant temperature has to be lower than 45 degrees, lower than 45 degrees. And in order for heat transfer to take place, the refrigerant has to be leaving the condenser at above, oops, sorry about that, above, what's happening here? ABOV, I'm going to cross that out, Brett, that's weird. At above 85 degrees Fahrenheit. And we're going to see what those temperatures might be. They don't have to be these exact temperatures. It all depends on how the chiller manufacturer builds this chiller. Okay, so let's add some more temperatures in there. So now we're seeing that the refrigerant temperature is 32 degrees in our simple example here. It may not be in the real world. Refrigerant might be slightly different in temperature, but you get the general idea. The refrigerant temperature has to be below the supply water temperature on as it enters the evaporator, and then as the refrigerant temperature has to be above the condenser water temperature here. So the temperatures that we're mostly interested in here are the refrigerant temperatures, because this determines how much work the compressor has to do. And if you'll notice, it doesn't matter which side of the condenser or evaporator that we're on. We're going to make sure that we have a low enough temperature. I can just cross out 42 for now. So our refrigerant temperature wants to be around 32, perhaps a little bit higher than that, and that's when we call it superheated, and that's to make sure that we have gas in the compressor. So the important thing is that the refrigerant, the compressor is trying to raise the temperature from 32 in both sides here, from 32 up to 105, and there is a pressure associated with those temperatures, And one last thing I want to point out is that when we talk about this, and the reason I spend a little extra time talking about this is because conceptually we want to make sure that everybody understands that the amount of work that the compressor has to do is a function of these temperatures, these guys right here. So if I can raise my chilled water temperature, that means that I can raise my refrigerant temperature, if I can lower my condenser water temperature, I can lower my refrigerant temperature at the high end, and that temperature difference and the pressure associated with that is called lift, L-I-F-T. So the compressor is adding pressure to the system as a function of these temperatures. And just for the fun of it, because we are going to examine a pH diagram, we're also going to add the enthalpies at these 4 points here. So here's the enthalpy. And let me just put in the rest of the number here. Whoops, let's go back here. So there is the enthalpy entering the compressor. We call it H1, leaving the compressors H2, leaving the condensers H3, and entering the evaporators H4. All right. So let's look at that in terms of a pressure enthalpy diagram. I'm not going to spend any time going through the details. I just have it mapped out here. This is our H1 value right here. That's entering the compressor. That's 175 BTUs per pound. Here's the enthalpy leaving the compressor. Here's the enthalpy entering the evaporator, and the enthalpy leaving the evaporator is the same as the enthalpy entering the compressor. And these numbers will help us understand how much energy this chiller is going to consume. And as it turns out, from this value here, H1 to H2, if you'll notice on the pressure enthalpy diagram, that starts right here and it ends over here. And the compression process, the process of the compressor, is called a constant entropy, otherwise known as isentropic compression. And then these lines are horizontal lines. These are lines of constant pressure as they relate to temperature. So here is our pressure related to the evaporator temperature, and this is the pressure, let's see, that's the pressure associated with the evaporator and the pressure associated with the condenser, constant pressure. So if I can increase my supply water temperature, let me erase these lines because it gets a little confusing here, just for the fun of it. If I can increase, if I move this line up, you can see, let's say I draw a line over here, all right, then now I have less work to do out here on my compressor, delta H. And if I can lower this line down here, you can see that that becomes even smaller. So the key to making a the key to making a chiller plant efficient is to try to get the supply water temperature as high as possible and the condenser water temperature as low as possible. Isn't that the coolest thing you ever saw?
Pretty cool. Pretty cool.
Pretty cool. Okay. So if we plug these numbers into these very simple equations, again, you're going to be able to have your recording so you can look at this little slide for as many hours as you like. But it turns out that the coefficient of performance is defined by the output divided by the input. And the output is the output of the evaporator, which is this value here. Input of the compressor is this value here. We just plug in the numbers that I had from that previous page, and we take the ratio of those two, 65 divided by 12.5. The ideal coefficient of performance is 5.2. And that's reduced by the actual COP also includes the compressor efficiency. And if we put in there an efficiency of 80%, then 80% or 5.2, which is this value from up here, times 0.8 is going to be equal to 4.16. The important thing to keep in mind is that, again, repeating what I said a moment ago, that the enthalpies are a function of temperature and pressure when it comes to the compressor and the evaporator. So the ideal coefficient of performance, the capacity essentially of the chiller, is a function of these temperatures and pressures, and they are independent of the compressor efficiency. As soon as you add the compressor efficiency, and that's when you talk about the actual coefficient of performance. So all the numbers that I presented to you right now show you that the best you could possibly do under this scenario of temperatures is 5.2, and then if you add the efficiency in there, and I just arbitrarily made 80%, if your efficiency was slightly higher than that, then your actual COP would be higher than a 4.16. But based on the numbers, you cannot get higher than 5.2 based on the temperatures and the pressures that I had listed in the pressure enthalpy diagram. So before I go into some of the other equipment, any questions, Brett, about how we got
just a couple of questions. I think you just covered this one, but someone just asked, what is the difference between chiller efficiency and COP? And I think you covered that pretty good just then. And then Paul is asking, do these temperatures depend on the refrigerant? And I'm sure the answer is yes. I think that Trane's central vac chiller may use R123. So it must have been back of slide or two.
Yeah, so the enthalpies will change because the pressures associated with the temperatures are a function of the refrigerant. However, what the key is that whatever the pressure is associated with that temperature, in other words, if you're trying to make 42-degree chilled water temperature and you're trying to get your refrigerant temperature as high as possible and still get heat transfer. So, I mean, if you could make the heat exchanger, basically a shell and tube heat exchanger. If you make that shell and tube heat exchanger large enough, instead of using 32 degrees, for example, maybe, I don't know how close you can get, maybe you do it at 40 degrees, which changes the numbers that you look up. But yeah, the enthalpies are a function of the refrigerant. But in terms of, it's still with the lower supply water temperature, more energy, higher condensed water temperature, more energy. So the whole idea of this little first part here was to try to get everybody oriented to the fact that it's the temperatures that are driving the efficiency or the energy consumption. That's probably a better way of looking at it. Any other questions, Brett?
Somebody asked, why didn't we use an evaporative condenser instead of a cooling tower? I mean, that's kind of open for discussion.
Yeah, I mean, as it turns out, an evaporative condenser is kind of a closed circuit cooling tower in a way. But cooling towers, open cell cooling towers, in terms of what we're talking about today, are the more efficient way of rejecting heat. Okay. We talked about the actual COP. One of these other weird values in the American system is called the energy efficiency ratio, or EER. And if you take the actual COP times this value here, 3.412, you remember that one. And then the EER, the energy efficiency ratio, is 14.2. Let's say, and the kW per ton is provided by the chiller manufacturer. You and I cannot come up with a number for the kW per ton. That would be, for example, peak load. You would get that from the chiller manufacturer, and I said that would be in a range. That's a fairly common value. You can get them that are lower, and you can get them that are higher. All right, cool stuff.
Yep.
All right, we talked about that. Now, the other thing that chiller manufacturers publish is called the Integrated Part Load Value, or IPLV. And the IPLV is a standard established by the American Heating and Refrigeration Institute, and it's standard 550-590. And what it's telling us is it's saying that, look, we know that chillers don't operate at peak energy consumption all the time. And the IPLV is a standard, and what they said was that they're going to look at the chiller performance for 100% load, 75% load, 50% load, and 25% load. And they're also going to, especially for water-cooled chillers, they're going to take those readings at different condenser water temperatures. 85 is the maximum, and then 75, they're taking credit for that, 65, and then it levels off at 65 down here. Okay, so now we're going to actually, and these values here, this is the A, B, and C values. This is the performance of the chiller at these reduced capacities. In other words, we're going to look at them in a moment, a value associated with a kW per ton value associated when the chillers is 75% load. Yeah, I'm sorry, 75% loaded at, I know it gets a little confusing, at a condenser water entering temperature of 75 degrees. So they're looking at two values at the same time, and that's how they calculate the IPLV. And so the actual calculation looks like this. The IPLV is equal to that 0.01, saying 1% of the time it's operating at 100% load. 0.42 or 42% of the time it's operating at 75% load. And let's see, at 50%, there it is, 50% load is at a 45%, and 25% load, 25% load is at 12% of the time. So now the only thing missing is, well, what does the chiller manufacturer publish for the A, B, C, and D values here? And so here are some numbers provided by a chiller manufacturer for those values. The A value is 0.75 kW per ton, 0.68 kW, 0.65, 0.64. And if we plug all of those wonderful numbers into the equation, the IPLV is 0.66 kW per ton. And chiller manufacturers use this value to compare the operating characteristics of one chiller versus another chiller. So the IPLV, again, stands for Integrated Part Load Value, and it's a standard established by the American Heating and Refrigeration Institute. It's not necessarily what your chiller plant is going to operate at, but it gives us, it's kind of like the sticker that's on the window of your car that says that, you know, here's the highway mileage, here's the city mileage, and here's the combined mileage per gallon. It's not the values when you buy a car, it's not what you're going to get because you're not driving your car based on that standard. So this is a standard by which chiller manufacturers can compare them. There is another value which is somewhat highlighted here. It's called the non-standard part load value, and that's what the N stands for, non-standard. So the IPLV is based on the standard, and the N is the non-standard. So the non-standard is customized for your chiller plant installation or design. So that's the difference between the IPLV and the NPLV.
That's as clear, very clear, very clear.
It's clear as mud.
Hey, can you go back one screen? One screen. Someone mentioned is questioning the fouling factor listed there. It seems kind of small, but this is from the AHRI standard, so we really don't control that, correct?
Yes, exactly. This is the number that they chose for using for applying their standard, and the actual fouling factor could be higher or lower depending on the actual equipment that's being used. But again, the standard has to be based on everybody using the same set of values. So every manufacturer that uses exactly the same set of values under these conditions will wind up with numbers that they can compare the IPLV of one machine versus another. Good stuff.
All right. Yep.
Okay. So let's, I'm going to actually skip over this. If we had, well, let's just go through it quickly. I'm careful. I want to be careful of our time here. So we want to go into the piping stuff after we go through the cooling towers and stuff. So if we have a 24 million BTUs per hour and we have a delta T of 12 degrees Fahrenheit, remember I said it should come out to 2 GPM per ton? Well, the total GPM that we're looking for is going to be equal to 1 ton of refrigeration is 12,000 BTUs per hour. So we got 2,000 tons. And if we plug that into that other equation we talked about earlier, comes out to 4,000 GPM. For 2,000 tons, 2 GPM per ton, it's 4,000 GPM. Cooling towers. I'm not going to spend a lot of time on cooling towers. There are two major categories of cooling towers. The one on the left is the open cell cooling tower, and that's when the water in the cooling tower is the same exact water that's being sent to the condenser, In a closed cell cooling tower, it has a heat exchanger inside, and the water that goes to the condenser comes from the heat exchanger. So the water that's used for evaporation, there's a little pump down here. The water is pumped up to the top of the tower. It trickles down through this heat exchanger. So the water that comes in contact with the air does not mix with the water that comes in contact with the water going out to the condenser. So closed cell cooling towers typically are used for relatively smaller applications. They're very popular, for example, for water source heat pump systems where you don't want the condenser water to mix. You don't want the condenser water, rather, to be exposed to the atmosphere, which could be problematic, sending that water to tiny condensers in air as water source heat pumps. But for cooling towers, for the majority of larger chiller plants, if it's a water-cooled system, chances are it's going to be an open cell cooling tower. So those are the differences between those two major categories of equipment. So what do they look like internally? Well, again, the open cell cooling tower evaporates the water that ultimately comes in contact. This is the water that comes out into the condenser. And the water that's in the closed cell tower does not come in contact with the evaporating water. And that goes through a set of tubes and fins, and that's the heat exchange. That's this guy here, the heat exchanger. Heat exchange. And then that water goes out to the condenser. So it does not mix or come in contact, is a better term, with the evaporating water. So that's the difference between an open cell and a closed cell tower. What are the advantages? Well, typically for an open cell tower, you get more efficiency, but you do have the water that you have to be careful of, because ultimately the water consumption by the tower has to include not only the evaporation, but also the fact that it comes in contact with the condenser, the actual condenser. Let's see, how are we doing here? There's a lot of material to cover in a short time.
It is.
So, okay. I'm putting this on the screen. I'm going to skip over it. If you get the recording, you can go through these numbers. The evaporation for our system, we said, was about 2,000 tons. And that means that we need about, for the evaporation, about 56 gallons per minute, roughly, of evaporating water. But that's not the only water that the cooling tower is going to consume. The cooling tower is going to consume I changed these numbers earlier today, and apparently I didn't save it, Brett.
I've been there.
I've been there
earlier today.
Yeah, so this is 0.5. This is actually 0.5%. I'll get rid of that. This is the blowdown's about 1%. Leakage is about 0.5%. And the evaporation is approximately 3%. So if you add those all up together, then it's going to be, let's see, that's going to be 2 and 3. So that's approximately equal to 5%. So somewhere between 4 to 5% is the amount of water that your cooling tower is going to consume. And in our oversimplified example, that's somewhere between 240 and 500 gallons per minute. That gives you a rough idea of how much water a cooling tower is going to consume based on our system of 2,000 tons. 2,000 tons. Okay. Good stuff. Now let's get into the really cool stuff, talking about pumps. So there are a variety of pumps that are available in terms of chiller plants. The end suction pump is a very popular pump, especially in the United States. The vertical inline is very popular in Canada, although I believe that the vertical inline is increasing in popularity in the United States, and I would expect in the next few years the vertical inlines will overcome the end suction in terms of a total number of pumps sold. Still, the end suction is still the greatest number of pumps out there. And the other category are horizontal split case. This is usually for much larger systems. These pumps can go up to 15,000 gallons per minute. Roughly the same for vertical split case pumps. I think they're a little bit less. I think they're, do you remember, Brett, how much these goes? I think they're up around 12, aren't they?
The verticals, yeah.
Around 12,000. We can look that up and we'll give you some more specific numbers. So those are the pumps. All right, I want to go into the piping because one of the topics that we wanted to talk about was the variable flow and the constant flow. So let's see what happens here. I'm going to switch over to a piping diagram. Hey, look at that, chiller plant piping options. Woo!
Almost seamless, baby, seamless.
We're going to talk about primary, secondary piping. We're also going to talk about variable primary flow. And then we're going to have questions. Again, ask the questions while we're going along here. The very first diagram that I have is a primary, secondary. So here in this diagram, we're showing the primary circuit down here. And I'm going to put a big P over here for primary. And then there is a bridge right here. Now that bridge is called a dozen different names. Sometimes it's called a hydraulic separator. It's also called a zero pressure bypass, closely spaced tees. There's 2 or 3 other names for them out there. But the important thing is that the primary, this piping system up here, go around the bridge here a moment, this represents the secondary circuit. So this is the primary circuit and this is the secondary circuit. So typically in a primary circuit, this primary circuit is constant flow. And in the secondary circuit, in a chilled water distribution system, this is variable flow. Now, let's assume that, again, this is a simple office building. There's nothing complex going on here. If that's the case, then chances are that we can reduce the flow on the secondary circuit, and usually the limiting factor is the pump itself. And so we say that the pump can go down to roughly one third its flow. But if you use multiple pumps, let's say if you use 2 pumps and each one was sized for 50% capacity, then that means that you're going to be half of 1/3 or 1/6 of flow. So you can see on the secondary side, you can reduce the flow significantly and save a huge amount of horsepower. On the primary side, you have to have constant flow. All right. So what are one of the pitfalls of primary, secondary? Well, one of the pitfalls is that you have to have 2 sets of pumps, one for the primary system and one for the secondary system. And you don't get the advantage of reducing the capacity of the primary pump, because in a primary secondary system, usually the main component, the chiller or the boiler, again, is looking for constant flow. What does just a primary pumping system look like? Let's go to the next one here. So this is a primary pumping system, and sometimes referred to as a variable primary flow. Now here the restriction is in terms of the minimum flow allowed by the chiller would typically be whatever the chiller manufacturer is telling us. Now, chiller manufacturers have a variety of ranges for chillers today, but let's assume for a moment, we're just picking a number, we know it's could be less, but let's assume that the chiller could go down to 50% flow, all right? And then if you use multiple chillers, in this case, it's only 1 chiller. If I use 2 chillers and each chiller was sized for 50% of capacity, then that means my flow in terms of the system could go down to 25%. So again, let's assume that I had a 2,000 ton system, just to put things in perspective, 2,000 tons, and if I had a 12-degree delta T, that would be 4,000 GPM. And if I had 2 chillers, then each chiller would be 2,000. And if each chiller could go down to 50% flow, that would be this value here, then that means it could go down to 1,000 GPM. And 1,000 divided by the total of 4,000 is now 25%. So the more chillers that you use in a variable primary flow, the greater the variation in flow. And so now you can see one of the advantages in order to optimize a chiller plant is to consider using multiple chillers because you can get the flow capacity quite low. And again, just for simplified, oversimplified examples, if I made 4 chillers at 25%, and then instead of the minimum flow for the entire system going to 25%, it would go to 12.5, which would be half again as much. So that's the major difference between a primary and variable primary flow and primary secondary systems. One of the advantages, you only need to have one set of pumps. Now, again, if we had multiple chillers, there's one there, there's one there. Well, let me erase some things. We're getting a little bit crowded here. So there's one chiller, 2 chillers, 3. I could use as many chillers as I wanted in any of these systems. And then I'd have multiple pumps. There's 1 pump, there's 2 pumps, 3 pumps. 1, 2, 3, 4, 1, 2, 3, 4. But I'd only have, for a variable primary flow, I'd have one set of pumps for the chilled water side, as opposed to back here. Whoops, I got too many lines drawn here. Let's see if I can erase that. In a primary secondary, if I had multiple chillers, I would have multiple pumps on the primary side and multiple pumps on the secondary side. So what we're seeing in terms of system configurations is that more and more new chiller plant designs are going with a variable, I hope I spelled that right, variable primary flow. And designed properly, you can reduce the amount of energy consumed. By using multiple chillers and multiple pumps, you can get that fraction quite low. Okay, we covered a lot of material. We did talk about primary, secondary flow, variable primary flow. We talked about water-cooled versus air-cooled chillers. And we talked about the different components and parts that are in a chiller plant. We covered a lot of material. Again, hopefully you can download this recording and you can go through some of the numbers that I presented to you by looking at some of these slides in more detail. But do we have any questions out there, Brett?
Yeah, we have a couple good questions. And the first one's pretty straightforward. Alex is asking, would you recommend using glycol or an electric heating coil to prevent freezing in open cell cooling towers?
Well, now most open cell cooling towers, they use a variety of techniques. The most popular is to use a basin heater in the cooling tower so that if you're running the cooling tower in the wintertime, especially if you're doing water-side economizer, sometimes referred to as free cooling, you're going to run the cooling tower in the wintertime, and to keep the basin of the tower from freezing, they use electric resistance heat inside the basin of the cooling tower. And then another technique, which has its pros and cons, is to allow the cooling tower to drain to a storage tank inside the building. And sometimes that's referred to as a remote sump for the cooling tower, in which case the water does not sit outside in the weather inside of a basin. As soon as the flow stops, the water immediately goes to a tank inside the building. There are pros and cons to that. One of the benefits is that you don't have to worry about heat tracing or insulating the piping on the return side of the cooling tower. You do have to insulate and heat trace the piping going out to the tower. The downside is that you have to have a tank physically inside the building, and that consumes a lot of space. And the other thing is that for most of these remote sump systems, you're draining from the cooling tower to the tank by gravity, which means that as far as the pump is concerned, the pump is taking water from a lower elevation, which could potentially be a problem with net positive suction.
Yeah, and I think glycol probably isn't used for that application, but maybe in a closed tower, cooling tower located outside, it would probably be glycol that would be used in the northern states or for
yeah, very good point. Yes, in an open cell cooling tower, you would not use glycol, and right. We should just state that.
Yeah,
but you're absolutely right, Brett. The closed cell uses glycol a lot,
right?
And then, sometimes. Go ahead.
There's one other question that we can cover in a short time. How do you deal with chiller? Well, we're going to have to give a quick answer. How do you deal with chiller cycling at low flows? Bypass, bypass, bypass. Hand controls.
Yeah, as it turns out, the issues with chillers short cycling, there's a whole series of problems to reconcile.
Right.
So we don't really have the time to go into all of those different issues, but I think to your point, Brett, is to properly sized bypass is the primary um, solution for keeping chillers from short cycling.
All right.
Well, actually, I should add to that. It's also the buffer tank.
Right.
Because chiller manufacturers will publish the minimum volume of water that they want in a system. And let's say that you had, again, using our 2,000-ton chiller plant, if we had 2,000 tons and the manufacturer wanted 5 gallons per ton, that means 10,000 gallons. If the piping system held, say, 6,000 gallons, then you would need 4,000 gallons of buffer storage to ensure that the chiller didn't short cycle. And that information comes from the chiller manufacturer. I picked a common number, 5 gallons per ton, but it could be slightly higher, it could be slightly lower. Check with the chiller manufacturer.
We're all set for questions. Our friend Kevin Lee says, very good presentation. Please do more like this. So we'll have to take that into consideration. So thank you, Rich. You want to say something before I sign off?
Well, thank you very much for participating in today's discussion. I realize that we went through it rather quickly, but again, one of the benefits of having a recording is that you can go back and you can look at these different slides and you can gain some information. There's lots of good information. So hopefully the recording will supplement what you heard today and give you time to absorb some of this. So thanks again. I'll turn it over to Brett. Take care.
Thanks, Rich. Appreciate it. Appreciate it, everybody. Look for your emails. And I think our next Takeo Tuesday isn't until 4 weeks from, I don't know when it is, sometime in November. I don't know. Look at the schedule. It might be the end of November, or it could be whatever. So coming up, look for the emails. Look for your email tomorrow. But other than that, thanks for your time and signing off from New England. Bye, all.